Computer app dyan. Ano ba yun?
Boy, everyone is so quiet this morning. Is it because it's a rainy day and we all want to go back to bed?
At least I do.
Mr. Brian.
You guessed it. Good morning, Mr. Brian.
Good morning. Kind of a cold, rainy day out.
Yeah. We are lucky that it's online, or else if it was in school, we have to wake up and go and drive,
Drive and it's cold there. Then we're out in the lab and it's cold. And
Yeah.
so,
Mr. Brian.
good morning. So there are some good things about being online. You get to stay home where it's warm and dry and don't have to drive on the road in the rain.
Correct.
We can even attend school in our pajamas.
That's right. And you can get a cup of coffee anytime. Yeah, Rudy.
Point two, homework that you give us. It's hard to read. It's too small. I have to enlarge it.
Well, good thing your computer can do that.
It's okay. I made it.
That's the nice thing about computers. When the writing's small, you just make it show up bigger on the screen. Because I have to do that too sometimes. I get to like 200% and I have a big screen.
I think you have a dual screen.
I have 3 screens.
Wow.
So before we started teaching online, I only had 1 screen. And then when I had to start teaching online, I did the research and found out they recommend having 3 screens. So I got more screens.
Morning.
So, we just have to adapt as things change. So today we're going to get more into fuel system. And then I'm going to let you guys out about 15 minutes early. So I know you're going to be rushed.
How did we deserve that?
Well, you deserve it because I have to do another one of those webinars today at 10 o'clock. And so I need to get my system changed over to the other platform, do all the checks, and hopefully take a quick break before I jump into an hour-and-a-half webinar I have to teach.
Sure. I have a question, Mr. Brian.
Yes.
I received the email and it says that Spring 2021 auto assignment graded 8.2.1 is graded.
Okay.
I never did that quiz. So how
it's probably graded because you didn't do it and it became due. I put a default grade of 0 there. So that's why I told you it was graded.
I don't want 0.
Well, then you need to do the assignment. That's easy.
Okay. Thank you.
So that goes through and lets you know that you missed an assignment. So that's why I do that. So if you have a 0 on an assignment, you could still do the assignment and turn it in and get full credit because I don't mark you down for being late. But it's my way of letting you know, hey, missed something. Easy to do.
I thought different way. I thought last semester, Mr. Fu class, I attended the same class, same subject, same quizzes. So I thought I got graded. So I was feeling
Yeah.
good side.
Yeah.
Thank you, sir.
Uh-huh. Okay. So that's why you guys get out 15 minutes early. I could have said it was because it's a rainy day.
I thought so. Yeah.
Maybe I should have gone with that. It would have sounded better, huh? I know I looked last night, they already had 117 people signed up for my webinar that I'm doing. So I had 140 something last time. lot of people. Okay, so I got the screen shared. And so I finished off yesterday with this question. If the octane rating is higher, what effect will this have on the temperature fuel ignites?
Higher.
At a higher temperature, number one, correct. So gasoline fuel engines perform best when used with the octane rating recommended by the manufacturer. So that's what the engineers designed for the vehicle to run on. That's what they're looking for. You can put higher octane in, and you're certainly not going to damage the vehicle. You may or may not get all the benefits of it. Putting lower octane in can damage the vehicle. Octane can be boosted with additives, so they do make some over-the-counter additives to help boost octane. Those additives fall in two categories. One is basically just adding alcohol, and the other one is a more involved chemical additive. Octane is now boosted with additives of ethanol, aromatic hydrocarbons, and other chemicals at the pump. So we don't really buy gasoline. We buy gasohol in California. So our gasoline is mixed with alcohol. Currently, it's at 10%. So it ranges between 5 and 10% in California. Right now, it's currently at 10. Mix of gasoline and alcohol, usually 87 octane gasoline, but we see that for all of our grades in California. Usually grain alcohol. Grain alcohol in the United States comes from corn. If I go to Brazil, it comes from sugar beets. They also use sugar cane for grain alcohol. Alcohol range on a vehicle ranges anywhere from a low of 2% to a high of 85%. So 85, if you have a flex fuel vehicle, your vehicle is designed to run on up to 85% alcohol in the fuel tank. If you do not have a flex fuel vehicle, your vehicle is designed to run with no more than 20% alcohol in the fuel tank. And so the blend we use here at the pump, so next time you go to the pump, you'll probably see a sticker, and that sticker is going to say E10, means the ethanol percentage is 10%. So if it was E5, it'd be 5%. If it was E85, it would be 85%. So E means ethanol, and then you have the number, meaning the percentage of ethanol in the fuel. We do something similar with diesel where we use biodiesel. And if it has biodiesel in the fuel, it have a B as in Bravo, and then a number indicating the percentage of biodiesel that's used. And manufacturers do not want any more than 20% biodiesel used. So alcohol does a couple things. So it increases the octane rating, so it allows manufacturers to spend less money on refining and then add alcohol to boost that up. Many stations sell it. Actually, in California, everyone sells gasohol. Engine and fuel modifications are not needed as long as we're running less than E20 or less. This is California gasoline across the board. This does present some issues, especially on older vehicles, and even where there are rubber components and the components inside of carburetors are not made to handle this alcohol, so they do not last like they used to. So we have a lot of issues there. Alcohol is also largely a political issue. One of the reasons being is it takes a gallon of fuel to produce a gallon of alcohol. So that doesn't seem to make a lot of sense. So you're basically feeling good about burning alcohol because it has less CO2 emissions, but we're probably burning diesel to make the alcohol.
Mr. Brian,
What's that?
Mr. Brian, good morning.
Good morning.
So alcohol isn't it is not based of water? I mean, like because do the gasoline mix with the alcohol, or can you actually?
Yeah, gasoline mixes with alcohol. Alcohol is not water. Alcohol can be used to disperse water. So if you have a car with some water in it, you can actually add alcohol, and the alcohol will attach itself to the water and help the water get out of the fuel system. And we use water to see if we have alcohol in the fuel, because the water will separate the alcohol back out. And you actually use a little test bottle and put a certain amount of fuel in with a certain amount of water, shake it up, let it sit, and see how it separates out. And that's what we do for testing to see if there's excessive amounts of alcohol in the fuel system. So we can measure the percentage of alcohol that way. And we're actually adding water to the little test bottle to do that. So alcohol can immerse with the water, and it'll actually capture it. And then we can also get it to separate back out because it has a different weight. Some fuel system additives, alcohol is designed to keep some of the water out of the fuel. I mean, so it's not like alcohol doesn't do any good things, but it is very hard on components, especially in the early days. Now modern vehicles are made to handle the higher octane alcohol content, so we don't see the same hose failures and injector problems and things that we did on early models.
Yeah. Okay. No, thank you, Mr. Ryan. So the E85 that we see on the gas station, that's what it means, right? So 85% ethanol.
85% ethanol, and and you can only use that in a flex fuel vehicle. If I put that in a regular vehicle, my car is going to stop running. Because the computer system can't handle it. And then the car doesn't run. Also, things like fuel pumps and other parts can actually be damaged.
So some cars can actually take it. No, I did. I used to have a 2000 Dodge Ram 5.9, and I did a test on my truck. So I put ethanol, and it was running. However, I did trips more often to the gas station than regular fuel.
Right, and then once you get over a certain level, you'll get fuel trim codes, and once you get to a certain level, the car will stop running. So it depends on how much alcohol is in there, because the fuel system can't compensate for it. But the E85, if you have a yellow gas cap on your car, it probably says E85 on it. Yellow gas caps are for flex fuel vehicles, letting you know that you can run the E85. So in E85, if you go to a gas station, E85 will probably be the cheapest fuel there. Usually by about $1 a gallon, which is pretty amazing. A lot of subsidies go there. But here's the deal. You get about a third less miles to the gallon. So you're paying less for the gas, but you're not going as far.
Yeah, at the end of the day, it's the same thing, or even worse.
Yeah. And that has to do with the stoichiometric ratio of alcohol compared to the stoichiometric ratio of gasoline. So stoichiometric meaning balance. So the perfect balance for air to fuel. When I am able to oxidize all of my hydrocarbon fuel, we call that a stoichiometric mixture. For gasoline, it's 14.7 pounds of air for every pound of fuel. For ethylene alcohol, it's 9 pounds of air for every pound of fuel. Well, since my engine is an air pump, you can see where I'm not going to be able to go as far on a gallon. So a gasohol mixture with 15% alcohol would be marked with which of the following labels?
2, E10.
Not E10.
Number 4.
15.
Number 4.
Wait, oh, 15.
Not number 4.
E85.
15.
Number 3. Remember, E stands for ethanol. The number is the percentage of alcohol that is in the fuel. So it would be number 3, E15.
Mr. Brian, question. So with
Yes.
regard to the octane rating of 87 at the gas pump, that means it has 75% gas and 10% I'm sorry, 12% alcohol or something?
No, don't confuse. Octane rating has to do with how the hydrocarbon molecules are bonded together. And that has to do with the 8 carbon molecules and the 17 hydrogen molecules that make up a gasoline, basically a gasoline molecule. So atoms. So we have 8 carbon atoms, 17 hydrogen atoms. That makes up a hydrocarbon, which is gasoline. So how those are bound together, how they bind them chemically together through heat and other sources determines its alcohol content. So if they're all in a straight line, it's real easy to pick off those hydrogen atoms, and the hydrogens get picked off first. If the carbon is bound together in blocks into a square where it's bound to itself in more than one place, that's much harder to break apart. So it gets into the actual chemistry and how, when we oxidize gasoline, how the hydrogen is attracted to the oxygen and how it's able to pull it off the carbon, and how that whole molecular process happens. That's our octane. Our gasoline, or our E number, our mixture number, is simply the percentage of alcohol that we have mixed with that gasoline. Although alcohol will affect the octane level, when you go at the pump, that octane level is just the octane level already calculated after they've added gasoline to alcohol, in this case at 10% in California. So your E number has nothing to do with the pump number that you see, because all the gas, whether you're buying 87, 89, or 91 in California, is going to have 10% alcohol currently.
All right.
Mr. Brian, didn't you say more or less the fuel is all the same? Just the octane has to do with the detonation, the detonation control.
Yeah, exactly. What it is as we move up octane and we start bonding those carbon atoms together more soundly, it's harder to break apart, so it resists being completely oxidized. So it takes more heat to do that in order for that bond to be broken, and that's why it resists pinging.
Mr. Brian?
Yeah.
I have a question. So, okay, so just let's go back to my truck again. I used to have a 2000 Dodge Ram. Dodge Dakota 5.9, right? So I had a big engine on the truck. I didn't spend that much gas though on the truck because the engine was capable, handling that weight, and I think
right.
A little bit more than what. So why the industry is actually focusing on getting more power out of a small engine when you have to pretty much stress the emissions and all that, instead of going to what the car, like in my case, if you put a bigger engine, you use less power. I'm assuming, depending how heavy you're on the gas pedal, but you'll be using probably less fuel than a small engine.
Well, no, you're actually using more fuel than a small engine, but you're right. A small engine is going to work harder with the same weight. But the issue is that, like with your truck, it's not full all the time. It spends most of its time empty. So because we have a stoichiometric mixture, and because we're pulling air through the engine, we're going to use a certain amount of fuel based on displacement. What they're really looking at is how much power can they get out of each cubic inch or cubic centimeter of the engine. So if we go back to the glory days of hot rods, the late 1960s, right? We made some really, really powerful cars. Very few of them made 1 horsepower for each cubic inch of displacement. So to put that in, terms today, my wife's 74 Nova, when it left the factory with a 350 cubic inch engine, made 142 horsepower with that big V8. Now, if I look at my Camry, which has a 2.5 liter engine, which is about 145 cubic inches, it makes 178 horsepower.
Yeah. So okay, so I see a little, I can see a little variable there, which is going to be either fuel injection or carburetor, because carburetor is going to be just putting fuel no matter what, you know, it's going to be
Right.
But injector is actually restricted by the computer to see how much
Yep.
fuel. So yeah, but yeah, it's just like, you know.
Yeah, see, when you have a bigger engine, you have more weight. You're going to, most people are going to put their foot into it more. So my wife's Nova that was sold as an economy car, right? Because it had the 2-barrel carburetor on it, and it didn't have a lot, even though it had the V8. Doesn't get nearly the mileage my Camry does. Well, why? One, the engine is, over twice the size. The other is that the car weighed a lot more. So we've lightened up cars a lot, and we're getting more power out of each cubic inch displacement. So we're more efficient. We're increasing our efficiency. And as we've done that, we don't need that really huge engine as much anymore. Is that to say there isn't some big engines out there? Absolutely. If you look at truck engines or you look at other stuff, there's still some big engines out there, because but yet you look at what they're able to pull now. If you look at an older pickup truck, it might only be able to pull 6,000, 8,000, 10,000 pounds. Some of these newer trucks pull over 20,000 or over 30,000 pounds. So, you've increased the capability of it while it still gets reasonable mileage out of that big engine, meaning that now you can do that with one trip instead of 2 trips. So, which is further saving on fuel economy. So am I thrilled about that? Hey, an F-150 comes with a 4-cylinder and a turbocharged engine, and that's supposed to be my pickup truck? No, I'm not real good with that. So don't, I still drive my old truck with a big V8. Is it the most efficient in the world? No, it's not. Does it pull a hill really good with a big trailer and a camper on it? Yes, it does. Does it haul the weight I need? Yes, it does. Is it as efficient as a newer car? No, it's not. So I don't fool myself into that. But on the other hand, it still does the job extremely well, has for over 30 years. And to replace it, it's a $50,000 truck. I'm not going to go do that.
Yeah, no, it's just that, with all the technology that we have nowadays, of course, if you're going to have a truck, small truck with a V8 and in it, but with all the good things that we have, which is, aluminum, more, you can say, electronics, it will be, I'm assuming it's going to be more efficient, than if you put a 4-cylinder on a truck instead of a V8.
Right.
Emissions, it's more pollution, no?
Yeah, because now if you look at a lot of truck beds are aluminum, we have aluminum frames. So I don't need, and that 4-cylinder is going to weigh half or less than half of what that V8 did. So if I can make close to the same horsepower, I still get that maximum load that you had before. But most of the time, what are you doing? You're driving around in the truck by yourself empty. And we know that, especially on a 150 or a half-ton truck. Or like you had a Durango or Dakota, which is that, quote unquote mini truck, which isn't that mini anymore. But you look at Toyota Tacomas, you can get a 4-cylinder engine or a 6-cylinder engine, right? That little Tacoma works fine with that 4-cylinder engine. So because how are people using that truck? Most of the time it's empty or it has a light load in it. They're not filling it up with a ton of gravel, or you wouldn't do that with that truck. So it it's kind of need based a lot. I do agree with you. As we push things closer to the limit, they tend not to last as long. That's why turbocharged engines have never lasted as long as non-turbocharged engines do. They run hotter. They're pushed tighter to the construction limits of the mechanical part of the engine. They just don't hold up as long. They just don't stay together as long. Because now we're forcing to get more power out of the same small container. Something's going to give. So you sacrifice longevity for all that performance. And, we don't see that as much on diesels. Diesels really respond well to turbocharging, but that's because they don't use spark plugs. There's a whole lot of other reasons. But gasoline engines, I could put a turbo on it or supercharger on it, but it's going to shorten the life of the engine.
Yeah. It's just, I mean, the industry is kind of like, you have, it's ups and downs, I mean.
Yep. Yeah, there's not one easy, always works great thing. Everything is a balance. So controlling fuel burn, a lean air fuel mixture has more air in proportion to the amount of fuel. So we call that lean. A slightly lean mixture gives good fuel economy and low exhaust emissions. A rich air fuel mixture has less air in proportion to the amount of fuel. And what I can tell you is this is what's in the book, and I kept it here. A slightly lean mixture, depending on the car, can cause huge exhaust emissions. So it really kind of comes down. So being slightly lean is not always good. We do run cars lean under some conditions where they will not make additional pollutants. So that's why we have an engine management system, because the book here is pretty rough, and we'll see here. So we have, when we look at rich and lean, we have our 14.7. A slightly rich mixture can produce more power, but the extra fuel it uses steps up consumption and greatly increases emissions. An extremely rich mixture can foul spark plugs, increase carbon deposits in the combustion chamber and exhaust. So I have a couple of things here. I have my fuel consumption and power, right? So there's a curve here, and we're way off the chart here. As you can see here, we start rolling. I have my carbon monoxide emission. Carbon monoxide, by definition, is a lack of air. So when I'm rich, which is to the left here, I don't have a lot of oxygen, so I'm going to have a high CO, and it goes down as we get lean. Now, keep in mind, there's three emissions we look at. There's carbon monoxide, hydrocarbons, and oxides of nitrogen. This chart is only showing you carbon monoxide, which is directly affected by the air fuel mixture. It's not showing you hydrocarbons, and it's not showing you NOx, both of which will elevate if the car goes lean, and hydrocarbons will elevate if the car goes rich. And I have charts coming up. We'll see that when we get into emissions. But it really is a balancing act. It's not as simple as we see here. On the top, we have a chart, and it says Lambda. And we're going to get more into Lambda in the fuel control PowerPoint. But Lambda is the ratio of oxygen available to oxygen required for complete combustion or complete oxidation of the hydrocarbon. So when I've matched all my carbon atoms and all my hydrogen atoms up with all the oxygen atoms and no one's left over, that's one lambda, when we've got that balance perfect. So in the chart here, they're showing you 0.9 to 1.1 and saying that's the normal operating range. It is not. The normal operating range of lambda, and we'll see it when we get to the fuel control section, is 0.980 to 1.020, substantially less than what the book shows you, right? Because they're saying it goes between 0.9000 to 1.100. That's totally wrong. The range that we operate is 0.980 to 1.020, and we actually operate in a tighter range. That's the outside of my limits that I'm allowed to operate. So this is really rough. We're going to really refine this more, but since the charts I'm going to show you in fuel control and the charts I'm going to show you in emissions bring this number way, way down, I wanted to point out that this is kind of wrong. But it is in the book, and that's why I left it in the PowerPoint. You can see where it does kind of give you the concept, though, that we need to balance our mixture so we get the right burn.
Mr. Brian?
Yes.
So there's not much wiggle room on this on the lambda compared to fuel trim percentage. Because I mean. Okay,
so fuel trim is used to keep lambda at the correct place. So I can use Lambda to double check that my fuel trim's working correctly. So I can use that to verify whether I have a sensor that's out of calibration or something like that. Because Lambda is taken by using a gas analyzer and taking the gases that come out of the tailpipe, plugging them into a Lambda calculator or doing the calculation by longhand, which I wouldn't wish on anybody. And it's going to give me that percentage number where my Lambda's at. And so if I have a car that, for example, has 25% positive fuel trim, meaning it's adding 25% injector on time, but my Lambda says the car's running rich, that tells me there's a problem with my fuel control system because the computer's adding fuel to get to one Lambda or close to it, but yet I'm running rich out the tailpipe. So do I have a bad sensor? What's going on here? Because the computer is making the car rich, and we can see it's rich, but it's adding fuel thinking it's actually compensating for something that's lean. So when we get in fuel control, we'll drill down that some more, Alberto. But that is because Lambda is what it is. And the other great thing about Lambda, and the reason why we use Lambda, is remember what I said, my ideal air-fuel ratio changes whether I'm burning straight gasoline, whether I'm burning alcohol over here at 9-to-1, straight gasoline at 14.7-to-1. But what happens when I put a mixture in? Well, now my ideal is going to be somewhere in the middle, correct? Because I mix the fuels. So a Lambda value of 1 for gasoline is a 14.7-to-1 ratio. Alcohol, a Lambda value of 1 means a 9.9-to-1 ratio. So because Lambda is balanced, as I mix fuels, we don't care what fuel we're using. A value of 1 Lambda is always a value of 1 Lambda. It's always perfectly balanced. So that gets me out of all these ratios. I don't care how much alcohol we have, what our percentage is, all that stuff, because that ratio no longer matters. Everything we do on the car is about Lambda. So it's all about, because Lambda, a perfectly balanced is 1.0 to infinity. That's a perfectly balanced system. And that balance is based on lining up all of my hydrocarbons with all my oxygen and the other gases, and everybody's accounted for. So at that point, does it really matter whether I got 5% or 20% or 85% alcohol? It doesn't. I'm just concerned with Lambda. That's what's going to tell me if my fuel system is working correctly. And so that is, we're going to drill down a lot more into Lambda, and that's why I have the fuel control PowerPoint. But since it's on the screen, I wanted to kind of explain what that is. They're lining it up to the air-fuel ratio as a linear thing where, hey, 1 Lambda is always 14.7-to-1. No, it's not. 1 Lambda is always 1 Lambda. Now, that ratio is going to change based on the fuel that we're burning. So, for example, 1 Lambda for hydrogen is over 30-to-1 if I'm burning hydrogen in an internal combustion engine. Propane is up somewhere around 17-to-1. So, again, depending on the gas I'm burning, my stoichiometric ratio, that's the pounds of air to pounds of fuel, changes. But when I'm in balance, Lambda is always 1. And that makes it really cool because now I can use that to see if I'm in balance or not, which is what the whole fuel system and whole computer system is trying to do, is trying to balance that. So that's why I don't really talk about air-fuel ratios, because to me they're not relevant other than knowing what that ratio is. It's really, from a diagnostic standpoint, it's all about the Lambda.
All right. Thank you, Ryan.
You bet. So the flame, I'm sorry, what?
Sorry, this is Del. Sorry.
Yeah, Del.
I have a question.
Yes.
What is the root word or origin of the word lambda, and how is it, I just want to know the correlation of that root to automotive or whatever. Why is it called lambda? I'm just curious.
No, great question. And if you could wait till I get to the fuel control PowerPoint, I've actually got a whole lot of information on that, because that's a great question. but I'd like to show you the PowerPoints I did to kind of explain that a little bit more.
Okie dokes, thanks.
But no, great question, Del. And we will get there. So flame spreads faster and moves evenly to halfway through the mixture. Combustion ends when the piston is a short way down the cylinder. And so that's going to depend on design. We now have the combustion doesn't end until the piston is more than halfway down. But we do want to end combustion, so because we've already accelerated that piston, there's no reason to burn past a certain point. So we can see before top dead center, the spark plug fires, the mixture ignites. Around top dead center, the flame front expands, cylinder pressure is rising. We're going to hit our maximum pressure shortly after top dead center, and then we're going to push that piston down. And what we're looking at here is right here, top dead center, this and this are in alignment. So if I have my maximum pressure, I'm going to put a lot of strain on these bearings. So what I want is I want them to where they're no longer aligned. So when I have my maximum pressure, we're now going to push down on this crank journal. It's going to move out to the side. So I've got leverage on the crankshaft. And so that is why we want to make sure we have that maximum pressure at the right time so we get the correct amount of leverage onto the crankshaft. What is the ratio for a stoichiometric fuel mixture for gasoline?
4.
Number 4, 14.7 pounds of air to 1 pound of fuel. And you guys go, why is he going over this so much? One of the things I get to do, I've probably mentioned this. If I have, I apologize, but I get to sit in on a licensing panel for instructors that want to be licensed to teach the SMOG program in California. And a lot of them put this 14.7 up in their presentation, and they don't know what it is. What's the ratio of gasoline to fuel? Okay, well, what do you mean ratio? Explain it to me. And I find they can't explain it. And these are people that are teaching. So if people that are teaching can't explain it or don't know what it is, or they normally go, well, it's parts. And I go, oh, so it's like cooking. So if I have 14.7 glasses of air, I need a glass of fuel. And they go, yeah. And I put it there. And then when they don't pass, I explain it's because I can't leave the parking lot because my car doesn't have enough gas at their ratio, and explain to them what it means. So it is because it's all about weight, and that's important because our engine management system is all about measuring the weight of the air. So that's why I harp on that so much. So detonation or pre-ignition. Detonation is a violent collision of flame fronts in the cylinder caused by uncontrolled combustion. Pre-ignition occurs before normal ignition. So pre-ignition happens when I have an alternate source that starts the flame, which will normally be carbon. The carbon will get glowing red hot and ignite my air fuel mixture before I want it ignited. Or it could be a high compression engine, overheating engine, something like that. So that's where octane can solve that problem. So if I have a pre-ignition problem, going to a higher octane where that fuel molecule is going to be stuck together better, is going to resist the tendency to ignite before I want it, and that's going to get rid of that pre-ignition or pinging. Detonation occurs after normal ignition. Can cause severe damage and must be avoided. Many engine management systems use NOx sensors to detect detonation. An engine that keeps running after it's switched off is said to be running on or dieseling. So some of you might have had an older carbureted vehicle. You turn the car off and it kind of go, and stop. And you put better gas in it and it stopped doing that. What causes that? There's only two things that can cause it. Either you're running too rich or your idle speed is too high when you shut the engine off. So I can run a very low idle speed as long as I lean out the mixture, or I can run I can run a high idle speed if I lean out the mixture, or I can run a low idle speed with a rich mixture. But I can't run a high idle speed with a rich mixture on an older car, like a carbureted vehicle, because it will diesel, it'll run on. About the only time gasoline, modern cars will diesel or run on is if they are severely overheated. Fuel injection, because the injectors are turned off, you shut the car off, will no longer do that. So if you are having a problem with it doing that, that's a sure sign that the engine is extremely overheated on a modern vehicle. So pre-ignition, a hot spot in the cylinder ignites the mixture before the spark plug, and detonation, a hot spot in the cylinder ignites the mixture after the spark plug, causing a second flame. I'm learning how to talk. Flame front. And what happens is if I have two flame fronts, now they're coming together, and when they collide, there's going to be fuel in the middle that never gets burned, as well as it's going to have those explosions colliding. Now puts extra force on the cylinder, and that's that noise that we'll hear. Detonation is also caused by over advancing the ignition timing. So if I start the combustion process too soon, so many times, and some books separate this differently, they're going to say pre-ignition is where something other than the spark plug started the fuel burning. Pre-ignition, it ignited before. Detonation is normally caused by over advancing the spark plug. So over advancing the ignition timing. So my spark is starting too soon. So my flame front expands while my piston's still going up, and that flame front hits the piston, which is detonation.
So Brian?
Yes.
So a couple questions. Okay. It's just that I'm trying to understand the situation here when it comes to compression, because I'm not really sure I got it. You know, I kind of make sense what my head is telling me. So, okay, if you want to do like a compression test, right? Or, the first puff is what it tells you what compression is on the cylinder, right?
Well, the first puff tells you if the rings are sealing well. It should be about half your final compression reading.
So, but I mean, like when the engine is running, it's only one compression. And then it pretty much makes the combustion, the detonation, and it makes the power stroke. So we can say that's pretty much one puff, right? Is that like we can pretty much compare it, kind of? Or
yeah, I think you can.
So now, okay, so if that pressure inside the cylinder is going to vary based on the RPM that you put it in, because if you test RPM, like if you crank the engine by hand, you're not going to have the same pressure as if you crank the engine with the starter, because the faster you do it, the less time the air is going to have to escape through the rings. So I thought that when you start the engine and the engine is running, if you have, let's say, 60 psi on the first puff, right? When you start the car and you do a running test, in my head I thought that since it's going to go run faster, it's going to be more than 60, because it's going to have less time for the air to escape from the piston ring. Am I missing something here?
Yes, you are.
On the test, I noticed that it was the same as when you crank the engine. I don't know why. What was it?
Okay. Great question. You're thinking this through. You forgot to account for the volume of the hose. That's why we have to crank it 5 times. Because when I have my compression gauge and hose, that is volume of air that's not part of my combustion chamber. So when my piston comes up on the first puff, we're measuring how much we compress, which should be half of my total compression. But I've increased the area I have to compress because I have this hose going all the way to the gauge. That's why we cycle it over 4 or 5 times as a minimum, so that I'm filling that gauge hose and actually getting the real pressure that I would see inside a combustion chamber. So same thing true with a running compression test. That's why we leave the Schrader valve in, and you'll watch it pump up about 5 times on a running compression test and then stop. So as I have volumetric efficiency, I am not pulling it at higher speed. I'm not pulling in as much air volume as I did at 200 RPM. But you're right, if I turn really slow, because of the rings in the leakage past the rings in other places, I am not going to get that high compression reading. So I need to have at least about 200 revolutions per minute to get a good compression reading. If I'm turning it over by hand, I can feel the pressure on my finger, but as the piston comes up and I hold my finger there, you'll feel pressure, then the pressure goes away. Go up a little bit more, you feel pressure, and the pressure goes away because that pressure is leaking past the end gaps of the rings, which is normal because our cylinder is not completely sealed, because of those end gaps in the rings. So we are going to get a little bit of pressure leakage past the rings. If you move it up slowly and put your finger on the spark plug hole with the spark plug out, you'll feel it build pressure and go away, build pressure and go away. And
so I'm assuming that the reason why they make you crank the car like 5 times is like a strategy, because if we compare that, the rotary engine, and the rotary engine is pretty much the first pulse that it counts. I mean, you crank the engine, you have to count the 3 pulses that it does based on the phase of the
on the rotor.
But it's only the first one where it counts. So you have to, in my case, I get a camera and I just put in a slow motion so I can see where everything occurs. But why is it different that on the piston that you have to do it 5 times? I mean,
well, you think about it. Each time a rotor goes around, you've had 3 compression cycles. My piston has to go up and down twice to get a compression cycle. So I want, so 2 crankshaft revolutions on a rotary engine. I've got 6 compression cycles on my compression gauge. In order to get 6 compression cycles on my compression gauge for my piston engine, I'd have to turn it over 12 times, which would be 6 movements on my gauge in order to get the same reading. That's why, that's why we see that big difference there, is because of the internal engine design. That's also why we have that Schrader valve at the bottom of the compression gauge, so it holds that pressure in the hose each time the piston goes back down and valve's open, because we have to fill that hose up with that high pressure air before we get a real reading. That's why we have to spin it over those multiple times. Otherwise, I've increased the volume I'm trying to compress, so now instead of 8 to 1, maybe I'm only 4 to 1 or 3 to 1. That's going to give me a very different pressure. And so it takes time for me to put that pressure into that hose to go into the gauge where we use that Schrader valve, so now I can get a real reading out of the cylinder.
So that means that means that so there is something missing when it comes to because when the manufacturer tells you to do a compression test on the rotary engine, they want you to take note of the RPM while you crank the engine, and based on that, you get the pressure. However, they don't mention that thank you for explaining that to me. That the hose, holds some pressure there. So that means the first pulse that we get from the rotary engine is not the correct one. I mean,
right? Yep. Yeah, and on piston engines, that's why they use a generic speed of 200 RPM, which is about the speed of good starter. So if I have a weak battery and my engine's cranking over slower, my compression gauge would show lower numbers on a piston engine. Right? So if it's cranking over real slow because I have a bad battery, I'm not going to get valid results for my compression test.
Yeah, and so based on on the now on going now to the detonation and preignition. So I mean, I can understand where the power happens once the spark plug fire. You have the power that push down the piston, but like you mentioned before. Burning, you cannot manage that time. It's just going to be the same time. For burning, there's nothing we can do about it. It's just, I mean, that's
right.
So at higher speed, I mean, I can understand when the car is idling because you have that time to push the piston down. But as the engine, the RPM gets higher, it's actually faster than the burning. So I'm assuming that you're using pretty much less power from the detonation. Is that what it is? Just a little.
Well, what you're doing is you're doing 2 things. You're advancing when you start the spark, right? We're advancing sooner, so we're going to start burning sooner. And our overall burn time will be a little less because of the volumetric efficiency. As you know, I have less pressure, which is less air. With less air, less fuel. If I'm burning less fuel and air, it takes less time.
But pretty much the limit is pretty much the top dead center, because you cannot go before that, right? Because if you go before that, then you have a problem because you're gonna go the opposite direction.
If I go towards what?
So the limit, I'm assuming the limit of the advancing will be pretty much top dead center. You cannot go.
No, because remember, normally we're before top dead center anyways at idle. And normally we advance between 20 and 30 degrees. So for my total advance. So if I'm at 5 degrees before top dead center, by the time I'm at my limit, 3,000, 3,500 RPM, I'm probably about 35 degrees before top dead center.
Yes. So when the piston comes down at high RPM, so first, when you are at idle, this guy fires, lower degrees of the for the spark to get to the spark plug. Now, high RPM that you mentioned, we advanced that, so we want the spark to go, before, a little bit, sooner to get, to top the center.
Right, because we want to have the pressure. Back up here. I want to have the pressure right here at the same place every time. So wherever the engineers designed that my maximum pressure in that combustion chamber should be at however many degrees this is after top dead center, and I've started going down, we're going to advance the timing so we always hit maximum pressure at that degree or very close to it as an engineering standpoint. And then once I run out of advance, if I continue to accelerate my engine, I start losing power because now, instead of my maximum pressure being here, maybe my maximum pressure is down here. Well, that's what? Less time to accelerate, bigger gas. So that's why when you have an engine over a certain speed, even though the engine is going faster, it seems to lose power.
Okay, so that's actually what that's what I was trying to get. Okay, I see. Yeah, okay.
So if I'm building a race engine that's always going to go that speed, I would need to reset my timing to account for that. And it might not idle. I might not be able to idle below 1,500 RPM. But now I can do 7,000 RPM, right? So that was something they used to do like with old V8. So that was between the cam timing, the ignition timing, all the other stuff in order to, hey, everything this car does is going fast for a quarter mile. And I need to do that at 7,000 RPM. So we're going to adjust everything so it's perfect at 7,000 RPM and sacrifice everything else, right? But if I have a car I'm driving on the street, that's not what I want. I want something that's going to give me good idle, is going to give me good power, but maybe I'm not going to get power over 4,000 RPM or 5,000 RPM. The engine may go a little faster than that, but we're going to start losing power slightly as it goes faster. Because what's the customer doing with it? What's the main purpose of the car? So we do that. Now, one of the things that distributor's ignition allows us to do is more infinite adjustments, right? So now I'm not limited by how far I can turn things. And now that I've gone with, a coil for each cylinder, I don't need to worry about my coil saturation time because each coil only fires once per cycle. It doesn't have to fire 8 times per cycle or 4 times per cycle. So now what? I can get to higher RPM because I have time to saturate the coil. Now the question is, do I have enough time in here to burn for the amount of fuel that's coming in? So that's why you see a lot of cars that do very high RPM have very small, normally cylinders. They may have 12 of them, but their displacement for the whole engine isn't that big. They just have a lot of very small cylinders. Well, so they're getting that volumetric efficiency. They're controlling the burn time. So there's a whole lot of math that goes into figuring this out and some science also, and certainly well above my pay grade. But it is interesting how they figure this out. But back to this is the only time I've ever seen detonation used with a second flame front. So it is interesting that they did that because carbon glowing carbon causes pre-ignition, not detonation, according to the ASE tests and that kind of stuff. So it's interesting that this book put it that way, because this is different than how I was always taught to distinguish it. And I know there's ASE tests asking me to distinguish those two things. And I know I got the question right because I got all the questions right on the test. So therefore I had to have gotten it right, even if I wasn't sure when I was taking the test. We all know how that goes. You're not sure, but if you get 100, hey, you must have been right. Cool. So it is interesting there. But detonation does occur after normal ignition. That is correct. And pre-ignition occurs before normal ignition. But detonation is actually normally the piston binding up more than a second flame front.
Mr. Perrin, question with regard to detonation. Isn't it picked up by a sensor, and doesn't PCM fix it?
Yes, it is picked up by a sensor, and the PCM adjusts for it by retarding the ignition timing. So by backing off the ignition timing, because detonation is normally caused by over advanced ignition, it'll do that. So even if it's pre-ignition caused by carbon deposits, the signal that the sensor will generate will be the same, so it'll still back off the ignition, trying to cool the cylinder. If that is not successful, many systems will start adding fuel to the mixture, because a richer mixture burns cooler. So that'll get rid of the detonation, but now fuel consumption and emissions are up. And that's why we get a code to let us know, hey, there's a problem here. Good question. You know, it's interesting. I was talking to a gentleman yesterday because we were talking about codes and computers. And he thinks that the check engine light is it's just there so, you know, mechanics can make money. It really doesn't do anything. And I said, well, why is that? He goes, well, my diesel truck, I took it in because the check engine light was on, and he spent a couple $1,000, and truck ran fine when it was done. It was running okay before. And 2 weeks later, the check engine light came on again, but his truck runs fine. So he thinks it's just a scam because there's nothing wrong with his truck. And I explained to him, no, there's something wrong with your truck. Your mechanic wasn't good enough to fix it. So your mechanic took your $2,000 and didn't fix the truck if the code you had before is the same code you had after you spent all the money. And he looked at me and goes, oh. But it is interesting because he's not the first person that said that, where a customer spent money on a code to make the check engine light go off. And after they've spent the money, the check engine light comes back on. And then the technician says, well, it's just an intermittent glitch. Your car is fine. Or it's just this and your car is fine. No, if the check engine light's on, the car's not fine. The check engine light's kind of like the tattletale on the mechanic, letting the customer know, hello, car not fixed. But it's interesting, the perception there that no, it's actually the light that's the problem, not the technician who worked on the vehicle.
Isn't it true that 9 times out of 10 that the check engine light is tied to emission? So even though you might not have a drivability issue, the car is trying to tell you that there's a possible emissions problem?
We are 90% right in that it's actually 10 out of 10 times it relates to emissions, because that's the only reason why that check engine light's allowed to be turned on. Other than that, you're 100% correct.
Mr. Brian?
Yes.
The other thing is actually, I want to say is bad marketing, because I don't know if you've seen the little plug that they sell that you put in your car, and that tells you exactly what's going on in your car. I mean, that's
right.
That's not right. And the other thing is when you go to the auto parts store, you know, they connect their scanner. They say, oh, you need this, you need this. You know, actually had people coming to me and say, hey, you know, I need this for my car. I say, I replace those parts. However, there's no warranty from me that the check-in is going to go away, you know, because I'm not buying those in the car. So, yeah.
No, that's true. We've made it too accessible, some ways too good, and too reliable. We're now, you know, it's funny because I've interviewed entry-level technicians, and they tell me how they have check engine lights down. They have them all figured out, and they got this code reader, and boy, they fix them left and right, and they're really good at check engine lights. And that tells me how much they don't know. You know, but that is the perception, right? If I got a code reader and I can get a code, now I can magically fix a car, because 80% of the time you probably are. So you feel really good about it without really understanding what's going on or how things work. And 80% might be high, maybe it's 70%, but you get the idea. I mean, you're going to fix a lot of stuff just because you're lucky and the code descriptions are pretty good of what area is bad. That's why people struggle with fuel evaporation codes, is because they're not just put this part on. They're hey, this system has a problem, figure it out. Fuel trim codes, people struggle with fuel trim codes because, again, it's not telling you what part's bad. It's saying the system's not operating correctly. Go figure it out. But if I have a code for an oxygen sensor heater, odds are the oxygen sensor is bad. If I have a code for an oxygen sensor not responding, odds are the oxygen sensor is bad. Or if I have a code for an EGR valve not working on many cars, odds are the EGR is bad, and so on. So there is a lot of codes that relate, directly to a component, but there's even more codes and more codes every year that relate to the logic of the system is not working properly. So if you don't understand the logic, you're not going to fix those cars. So it is something, but no, Christopher is right. 100% of the time, by law, the only time that light can come on is if it has to do with the emissions. So it doesn't matter if it's a transmission code. It doesn't matter what it is. It has to do with emissions. Because think about it. If my transmission no longer has overdrive, isn't that going to cause me to use more gas? If I use more gas, doesn't that increase the emissions my car makes? So everything that turns that check engine light on, it has to do with emissions. That's why we have other lights.
So, Mr. Brian, am I understanding it correctly that when the technician or wherever you take your car for repairs for engine light coming on, if that stays on, there's really something wrong with the car or the engine?
Yep. Uh-huh.
Okay.
Absolutely. Yeah, there is no, on modern vehicles, OBD2 vehicles, there is no intermittent problems. And we're going to go through and see exactly how OBD2 works. And I'll explain that to you. So we'll see when we get in the engine management, which is our next module, I think.
All right. Thanks.
You bet. So we'll see that some of the things we've been told might not have been true. They might just have been someone who didn't know how it worked and couldn't fix it. And they gave us something to feel good so that they could keep our money and go on.
What's the difference, Mr. Rob?
He put knowledge in there. So really, mechanic is what we all used to be called. As computers started coming into cars and things became more involved, the name changed to technician. Because technician really understands the logic and function of the components, not just how to replace the components. So there's a lot of mechanics that replace the components. There's not many technicians that understand and can diagnose the components as well as replace them.
So are we saying it's better to call them mechanics now? I mean, technicians now than mechanics?
Yep. Yeah, that name change probably happened 30 years ago, but we're a bunch of Neanderthals, so we don't really evolve quickly. But yeah, that's where all the licensing and everything else is all now technician.
I see.
So like it's a master technician certification, not a master mechanic certification.
Okay, so will it be like offensive because somebody mechanic now?
No, not really.
Oh, good. Just want to be politically correct sometimes.
Yeah, mechanics don't tend to be politically correct and they don't read the memos, so they kind of answer to anything.
I see.
Yeah, but only if they're deserving of the name, because if you took it there and they didn't remedy the issue, probably they're a mechanic and not a technician.
And you might not even want to call him a mechanic.
Exactly.
If you want to insult him, you call him a parts changer.
Wow, that's even lower.
That's lower. That means all you do is change your parts changer. So if you have someone, and we'll do this in the shop because mechanics are pretty mean to each other. You have someone that, it is not diagnosing cars correctly and putting on parts or just putting on parts. Call them a parts changer. It's that's the insult right there. That means all you can do is change parts. You're just a stupid parts changer. Oh, man. So that's mechanic insult there.
Good to know.
So we talked about dieseling already. Older cars used a solenoid to close the throttle to below idle position. So that was going back to carburetors. Fuel injected vehicles do not experience dieseling unless there is a leaking injector when the ignition's turned off or the vehicle is being severely overheated. So one of the essential components of the internal combustion engine is air. So we kind of take air for granted. We don't think of air as part of our fuel. But when I want to send a rocket into space, what do I need? I need a tank of fuel and a tank of what? Liquid oxygen. So oxygen is part of our fuel. And that's why I say we have a three-legged stool. I have, fuel, spark, compression. Those are the three things I need. Then I've got to put them together at the right time. So fuel is not just what we put in the tank. Fuel is also what we're putting in our induction system, the air. And I know someone brought up fires when we were talking about engine temperature. And really what's a bigger issue for engines is that fires consume all the oxygen and your car might not have good power because there's not enough oxygen. Again, oxygen is fuel. Nitrogen is the largest component of air. It's considered inert. Inert means it does not react with other chemicals as a rule. Oxygen is a highly reactive gas that promotes combustion. So that's why we say we oxidize things. If I oxidize something in the combustion chamber or oxidize it in the catalytic converter, that means I'm burning it. Argon and carbon dioxide are trace elements of the air. So you see very, 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 very small amounts. And these are the four primary things we see. Argon is also an inert gas. We use that for welding. Carbon dioxide we use for quite a few things. You can see very, very small amounts. So as I look at my air fuel ratio of 14.71 pounds of air for 1 pound of fuel, I have 7 gases that come out of the tailpipe. We measure 5 of them. We don't measure nitrogen because we have a lot of nitrogen that goes in the engine and out of the engine. It's inert. It's just along for the ride. It takes up space. My car also produces a lot of water. For every gallon of gas we burn, we produce about a gallon of water. So that's why in the morning when you start the car up, you get water dripping out of the tailpipe. You may see steam coming out of the tailpipe. Once the exhaust system warms up, that water is going to leave the exhaust pipe as a vapor and we're not going to see it. Hydrocarbons is fuel. So that is fuel that has gone into the engine, has not been burned, has left the engine, and is now suspended in the atmosphere. Carbon dioxide, CO2, is where we combine carbon and oxygen. And we want CO2 when it comes to cars. I know all the news says we don't. Cars run best and are most efficient when I'm making the most CO2.
One question, sir.
Yes.
If it is not too early, but nitrogen trucks, I saw the liquidated nitrogen. Where is the application, by the way? I saw the many trucks carrying the nitrogen, liquid nitrogen.
Oh, liquid nitrogen?
Yeah.
Oh, we don't use that in automotive. We use liquid nitrogen for cooling things.
So what is the reaction? Because it is, you said it is inert like argon and nitrogen. There is no reaction.
Right, but in its liquid state, because it has to get very, very cold to be liquid, they use it for keeping things cold.
Okay, okay, I got you. Thank you.
Yeah, so we're not burning it, we're just keeping things really cold. So CO, carbon monoxide. A lot of us have heard that because it's deadly. We have to have carbon monoxide detectors in our house. It's odorless and colorless. And so our car, if it's not running right, will make carbon monoxide. I can also have oxygen come out the tailpipe. That is just straight oxygen that we pulled out of the air. And I can have oxides of nitrogen or NOx come out the tailpipe. That's where I've had excessive heat and temperature and pressure to bond my nitrogen and oxygen that are in the air together. And that has to be under pressure and over 2,500 degrees, and that'll form NOx. And NOx is normally formed, one of the most common things that forms NOx is a lean mixture, although there are other things that can cause it. So these are the gases. We measure hydrocarbons, CO2, CO, O2, and NOx. These are the 5 gases that we currently measure. So there is no standard for O2 or CO2. We use those for diagnostic purposes. And there are state standards for hydrocarbon, carbon monoxide, and oxides of nitrogen. And those have standards. So when a car gets smog, if it gets a tailpipe test, those are the things we measure. So,
Mr. Bryan, did you say that you need a lean or a rich mixture to create excessive NOx?
and NOx can be created by a lean mixture because a lean mixture burns hotter and therefore we're more likely to form NOx. So there's other things that have to happen, and nothing works in a vacuum. But one of the problems with lean mixtures is NOx is formed.
Thank you.
You bet. And we don't see NOx as much in a rich mixture because it's a cooler mixture, and NOx is directly related to temperature. So I think it's good to kind of see how we're mixing everything together. You didn't know we're going to have chemistry class today.
Yeah, Mr. Bryan.
Yeah.
Sorry, I'm a curious person.
No, I know. It's great.
Why is nitrogen and oxygen combined, not NOx2? Well,
okay. So, great question. The reason why it's NOx is it can be any number of oxygen molecules attached to the nitrogen. Normally it's NO3 is the most common, but it can be anywhere from NO on up. So it could be NO, NO2, NO3, and so on. So they use the X there because there's not a defined number of oxygen molecules attached to the nitrogen molecule to make the gas.
I see. Okay.
Great question.
Thank you. Sorry. My curious mind is always asking questions.
No, and that's a great question. Why do we have an X there instead of a number? It's because it's an undefined number of oxygen atoms. That's why we use the X. So stoichiometric ratio, we've talked about this already, describes the chemically correct air-fuel ratio necessary to achieve complete combustion. For gasoline fuel, stoichiometric air-fuel ratio is 14.7 parts air to 1 part fuel by mass. Weight, I left this here because at least the book mentions weight. So they use mass, which is confusing. It's not mass, really, because we think of mass as volume, not weight, so it's confusion. But at least they define it as weight. The last book the school used just said parts and left it at that. It was just completely wrong. A mixture with a lower lambda value has proportionally less air than fuel. an exhaust gas sensor is used to indicate the amount of oxygen in the exhaust. So we do have an exhaust gas sensor. We call them oxygen sensors. They really don't measure oxygen. And we'll get to that. But that's another one of our little conundrums. They're actually a lambda sensor. The problem is when they came here in the 1970s, Bubba didn't know what lambda was, and he'd heard of oxygen. So domestic manufacturers, and consequently what's sold in the U.S., they're called oxygen sensors. But if you read early European service manuals, they'll all call them a lambda sensor, and they did that even up through the 80s because that's where these sensors came from, and that's what they're called. So, but, you know, Americans didn't know lambda then. Hey, oxygen, okay, get it. And it's a small difference. I mean, they kind of tell the computer the same thing, what's the mixture? But there is a difference as we get into more advanced level things, really is a game changer. And so instead of just giving you the wrong information now, and those of you that might go into this as a career, you can struggle for 5 or 10 years and then finally figure out I lied to you or the book lied to you. I'd rather just explain it now. And so we'll go through that in the field control and explain that a little bit better.
Mr. Brian, excuse me. What is stoichiometric? I don't understand that word.
Okay, stoichiometric is balance. So when we say a mixture is stoichiometric, that means that the oxygen is balanced with the hydrocarbon that we want to burn. And I have the same number of atoms so I can match up to make the molecules I should have coming out. No one's left over.
And why is that important?
Okay, if I'm not in a stoichiometric mixture or close to it, then I would have oxygen left over. And you're thinking, well, what would be so bad that you had oxygen over? Well, if I'm lean, which is the only way I can get oxygen left over, then I would also have hydrocarbons left over because I put enough of everything in for everybody to be balanced. So if I put a lean mixture in, now I put in more oxygen and not enough fuel. So it's like having a dance. And some people don't have anyone to dance with, so they're going to leave the party unhappy. So I need to balance it out so that all the atoms are able to line up and make the chemicals we want. And the chemicals I really want are water and carbon dioxide. So if I'm out of balance, if I'm not at a stoichiometric ratio and I'm running lean, I'm going to end up with oxides of nitrogen. I could end up with hydrocarbons, and I could end up with O2, and I don't want excessive amounts of that. If I am rich, then I would have excessive amounts of CO, excessive amounts of hydrocarbon. So in order to not pollute, I need to balance my air-fuel mixture where it is really in a very, very narrow range, so that way any emissions that come out of the engine that I don't want, my after treatment system, my catalytic converter, can clean those up. So we're putting clean air back into the air.
Oh, okay. Thank you, Mr. Brian.
You bet.
Mr. Brian, is there a filter in the intake manifold for the air that goes in? Because there is a catalytic converter for the exhaust, but what about for the air coming in?
Okay, so two points here. First of all, we do have an air filter. It's not in the intake manifold. It's going to be in the air filter housing that filters air coming in the engine because we don't want dirt and debris in. And second of all, the catalytic converter is not a filter. So it is a device that we have a chemical reaction in, but it is not a filter. Now, so all cars do have an air filter. And so it's not mounted in the intake manifold, but it's going to be mounted in the air intake system. And that's one of the things we change as normal maintenance, normally every 15 or 30,000 miles.
Okay.
So the density of air is its mass per unit volume. The volume of air at high density has higher mass than the same volume at low density. So what affects density? Well, atmospheric changes, right? temperatures, altitudes, all those things affect density. So that's why I say the computer is all about measuring how much the air weighs so I can put the correct amount of fuel in. So when we talk about Lambda here, I do have some stuff in here on Lambda. So Lambda is oxygen balance and oxygen available to combustibles demand for oxygen. So oxygen available to oxygen required. And this is a formula that was generated back in the 1970s. And I got the formula coming up, I'll show you. But a lambda ratio of O2 available for combustion process versus the combustible's demand for oxygen to attain complete oxidation. Lambda is equal to 1 when the O2 and combustible demand for O2 are in balance, the perfect stoichiometric point. Lambda control is necessary for peak combustion efficiency. Lambda control is necessary for peak cat efficiency. So 1 lambda and a stoichiometric ratio are the same thing. However, the stoichiometric ratio is fixed. So if I say the stoichiometric ratio for gasoline, that's 14.7 to 1. But I want to burn my gas at 1 lambda, and when it's at 1 lambda, I'm at a stoichiometric ratio, even if that's not 14.7 to 1, because I've mixed that gasoline with something else. Lambda control is necessary for peak converter efficiency. In other words, my catalytic converter won't work if my lambda is wrong. Lambda control improves reliability, fuel economy, and lowers emissions. So engine out combustion efficiency for gasoline fuel is no better than about 95%. So I burn 95% of my fuel in the engine. Tail out combustion efficiency for cat equipped vehicles improves to 99 to 99.5%. A factor of 10 improvement. Required for current emission standards, the catalytic converter, or CAT as we affectionately call it, combustion efficiency, that's the CE, is very lambda dependent. So if my lambda is not right, my CAT won't work. It can't.
Mr. Brian?
Yeah.
So the fuel trims pretty much, they work to keep the oxygen sensor close to stoichiometric.
No, not quite. Let's hold off on fuel trim till I get to the fuel trim slides.
I'm just trying to compare that with the lambda, because it seems to me that the fuel trims work to keep the lambda pretty much close, like pretty much on 1, right?
Correct.
So my question is, even though if you have can you have more than 10% of fuel trim to keep the stoichiometric lambda like
yeah
1?
Oh yeah, you could use 70% fuel trim to keep lambda at 1. Lambda is going to be close to 1, and the reason why I use close to 1 is some manufacturers manage their systems down at 0.994 to 998. Other manufacturers manage their system at 1.002. And that's why I use the term close to 1, because we're talking thousandths of a percent here. So very, very close to 1. As long as there is fuel trim available, the car is in fuel control. So even if I'm adding 20%, 30%, 40%, as long as I haven't maxed out the computer's ability to manage fuel, as long as I can still switch the O2 sensor between rich, lean, we're in fuel control, and we should be running close to 1 lambda.
The reason why I'm asking is because it seems to me that on the a system that uses a lambda sensor, it's going to be okay, running at 50% of the fuel, on the fuel trims. But when a car that uses the oxygen sensor, 15% is too much, and it will probably say your code. No,
well, they're going to set, cars will set a code as little as 5%. Setting a code is different than still running at 1 lambda, because keep in mind, we want that car to come in and get fixed before it's actually polluting. Right? So if I say, you know what, I don't want you using any more than 10%, and you come back to me and go, Yeah, I'm using 15%, but I'm doing a perfect job. Well, we still have a problem because you shouldn't have to use 15%. That's what sets the code. So you can still be doing a perfect job with 15%, but you're going to get a code because the engineer said, nope, you're not allowed to use more than 10. So let me get more into that when I get into my slides on fuel control and fuel trim, because I know we have some people that are lost on this, Alberto, and I know this is something that you're really curious about. And I promise you, I got a bunch of slides. We're going to spend a lot of time on it, but I don't want to lose everybody else while we're talking.
Okay, no, thank you, Mr. Ryan.
So a balance equation calculates lambda. So this, was it Breitenschneider lambda equation? Breitenschneider is a German scientist or engineer that came up with this lambda formula. As what lambda stands for, I don't know where he got that name, because I know that was kind of your question earlier, and I know, the German scientist, he came up with this formula, and in order to use the formula, I can do it two ways. Either I can do the math, or I can put the numbers that I get from a tailpipe reading and just plug those numbers into a calculator, and it's going to give me. The reason why I show the calculation here is because it accounts for all the different gases that we're measuring. So what we're doing is we're at the tailpipe, measuring the gases coming out. We're going to plug those gases into this formula, and based on those numbers, I can tell whether that car is running rich or lean by looking at the lambda number. So it's since I don't have a scale of how many pounds of air are coming in the engine or how many pounds of fuel are coming in the engine, what I can do as a technician is go to the tailpipe and look at what comes out, take those measurements, plug it into this formula, and now I know exactly how this car is running, rich, lean, and so on. So I am glad that they have a lambda calculator, because I would not want to have to do this, much less do this every day. But I do show it here to show that it really is a very, very involved formula. When you're looking at the atomic ratio of hydrogen and the atomic ratio of oxygen, I'm sorry, I didn't stay in school long enough to learn all this.
I already feel like we're not in an automotive or auto tech class. Seems like we're in a physics or whatever.
Yeah, isn't that interesting, though? Because a lot of people think of auto mechanics sometimes as, that's that dumb guy that's really nice that fixes my car. I think a lot of people don't realize what's involved to actually really understand and fix modern vehicles.
Correct.
It's mind blowing.
Yeah. Not bad for people that drag their knuckles when they walk.
So I feel like lambada is just missing one letter to make it a dance. I mean, lambda.
Yeah. It is interesting. And what's fascinating is this is something that wasn't introduced to us in the US really from a diagnostic standpoint or a calculator until about 15 years ago. So this is fairly recent, even though Volvo used it on US vehicles going back to the 70s. US technician training didn't start using it until about 15 years ago. And I actually did a 5-gas analyzing class. I've done it twice on webinars, and I'm doing it nationally. So once I get out of California, it's amazing how many people outside of California have never heard of it. Right?
I've never heard of it, Mr.
Yeah.
Ryan. So in our day-to-day lives, when will we ever hear this?
In your day-to-day life, you'll probably never hear it. Where you might want to know it is if you have an older car that fails smog, where they did a tailpipe reading, and the very first thing we need to do is do a lambda calculation to see how your car is running. If not, people just start putting parts on it and don't fix the car.
You mentioned older model cars. So what year are we talking about?
We're talking basically 99 and older.
Okay, thank you.
You bet. There are some newer exceptions, but that's heavier duty trucks and things like that. So, but now I can still use it for diagnosis on newer cars. But as far as something that, if you're not in this business professionally, back to Dell's question, where would this knowledge benefit me? Well, if I have an old car and I take it in for smog and it fails, before the guy tries to sell me all these different parts, the first thing we do is run a Lambda calculation, because we need to know, is the car in fuel control? Because if it's not, stop, fix the fuel control. I don't want to hear about the catalytic converter. I don't want to hear about spark plugs. I don't want to hear about anything else until we get the car running like it's supposed to run.
So the first thing you do is take a tailpipe analyzer. Not everyone has a tailpipe.
Right. No, but here's the deal, Rob. So you're 95. You go get it smogged and say it fails. You're going to get a printout with the gas readings from when it failed. You plug those gas readings into a calculator and then you know. And I'll walk through how to do this.
Okay, thanks.
So are you saying, Mr. Brian, that there is a specific calculator that solves this equation?
Yep, and I think I have it in my next PowerPoint, not in this one, because I kind of introduced you guys to it in this. Oh, no, I do have some calculator pictures in this one. Okay. I kind of blended the presentations together some, and I couldn't remember how much I did.
And the Brett Schneider, is he the scientist?
Yeah, engineer or scientist, from what I understand, because it's named after him, so I'm assuming as much.
He came up with this equation?
Yep, in the 1970s.
And named it lambda?
Yep.
Is this the point that you said will give us the origin of the name lambda?
Yeah, see, lambda, I believe, because you see the symbol, back up here, the symbol here, right here for lambda is Greek, I believe. So I believe it goes back to the Greeks and lambda meaning balance, I believe. And you can Google me to see how wrong I am. But my understanding is it goes back to the origin. And the reason why I chose lambda is the Greek symbol. And from what I understand, that means balance.
Okay, I will Google it. Thank you.
Google it, and you'll. And if I'm wrong, I won't be wrong next class because you'll tell me I'm wrong.
Okay.
I learn something every class, and you're the first person who's asked it. So I believe I'm correct, but I'll be curious if I'm not. So I'm good. I'm okay to be wrong.
Okay, that's good.
Brian.
Yeah.
There's also a Lambda car, right?
No, I've never heard of a Lambda car.
Really? I heard it's like an expensive car.
Well, there's a Lamborghini. And so sometimes they do abbreviate that down, but it's spelled different. But yes.
Mr. Brian, can the local smog shop, do they have the ability to get those tailpipe readings without going through an entire smog certification process?
Yes, they do. However, you're always better off just doing the smog test, because the smogs are done under load on the dynamometer, and that load is not going to be the same when they pull the tailpipe readings as the tailpipe readings are going to be when it's actually doing the test. They do have a mode on the machine that's supposed to simulate it. My experience is close, but not quite. And you definitely get different gas readings. And the other side of that is if it passes, it passes. So you'd hate to have, hey, my numbers look good. Now let's run a test, and it fails. And now you're paying twice and you still don't have a cert.
So is there a penalty to failing such that instead of every 2 years, you have to do it every 1 year?
No, with how the program is designed right now, and because if you have an older vehicle, 99 and older, it's directed automatically to a STAR station anyways, because they're the only ones required to have the equipment. There is no penalty. There's no downside to having your car tested. I do see a lot of downside when people try to do a partial pre-inspection or look at one thing and then eventually it doesn't pass. And the other issue, we get into some of the cost limits and some of the consumer assistance programs, none of which go into effect until after the car's failed the first time. So you could spend a lot of money on a car, still have something that might not pass. And if it never got a test, it's like nothing has been spent. So at this point in the program, there's no benefit, regardless of the year of your vehicle, not to just get it smogged. When I take my 87 truck in that I haven't smogged in 2 years to get smogged, and I drive it down to the shop to smog it, I don't pre-probe it. I don't do anything. I just run the test. It's either going to pass or it's going to fail.
Okay, thanks.
And I did the same thing with my Jeep. So it's either, if it fails, I'm going to fix it. If it passes, I'm done. So I just give me a baseline test and then I know where I'm at.
Mr. Brian, there are smog stations that's advertise, come to us and we'll make you pass.
Yeah. For enough money, you can get anything to pass.
It's underhanded.
What's that?
It's dishonest.
It can be on one way or another. Either I'm leading you to believe that, hey, I'm going to magically get your car passed, when in reality, I'm just going to fix it and then it costs what it costs. Or I'm going to take your money and fraudulently pass your car, in which case we all suffer because now your car's not fixed, you're out the money, and we're all breathing dirtier air. So neither of those are a good solution. Any car can get through smog. It's just a matter of time and money. There are provisions that limit how much money has to be spent under some circumstances. And we'll go through some of that.
I have a question regarding that, Mr. Brian.
Okay.
So when a smog place would pass you, fraudulently, like you said, aren't they getting caught by anybody or any,
Sometimes. Sometimes. So it is a misdemeanor. Penalty is $5,000 per vehicle, both to the technician and to the shop. And there have been cases where not only have they gone after them administratively and fined them, there's also been cases where people have been put in jail.
Okay, so it's illegal.
It is illegal.
California.
But so is driving at 100 down the freeway. Right? I mean, so a lot of times when we talk about smog, people go, well, I know someone who did this, or I know this. I only deal with what's legal or illegal. And it's my job as an instructor to tell you, what the speed limit in front of the school is 25 miles an hour. When someone comes in and says, hey man, I went down in front of the school at 50 miles an hour and nothing happened to me. Okay. Doesn't make it legal, doesn't make it the right thing to do, just means someone got away with it. Do people get away with it? Absolutely. The state spends a lot of money and a lot of research figuring out new ways to catch people that are cheating. At the same time, people that are cheating spend a lot of time and a lot of money trying to find new ways to cheat. So it is a cat and mouse game, and I know a lot of the ways that the state catches them. So I'm very fortunate that I get to see behind the scenes on some of the stuff they're doing that most people don't get to see, because some of the meetings that I do trainings in for Bureau employees, they're discussing some of these things, and I'm allowed to sit through the meeting and I'm instructed what I can and can't tell. But it does give me an idea of how things are going and what direction they're going in, so I can better teach technicians on how things work. And so I'm lucky to have that opportunity, and I make sure not to abuse it.
Brian?
Yeah.
Can I ask you a general question about the...
You have to sit closer. I can hardly hear you.
So, okay, so it's going to be just a general question. Can I modify a car and make it legal when it comes to emissions? Like, let's say, can I just put a different engine on a car and make it legal to pass emissions? So it's definitely a no-no here in California.
No, you can, as long as you follow the engine change guidelines. And the Bureau publishes the engine change guidelines. They're in the smog check manual. Actually, they're in the smog check reference guide. So that's all published. You just have to follow the rules. So it's not that you can't do things. There's certainly some things you can't do, but you just have to follow the guidelines. And the big thing is understanding what the guidelines are before you get started. The mistake a lot of people make is they start a project that doesn't meet the guidelines. Then after they spend a lot of time and a lot of money, they're upset that the state won't approve their project. If you're looking at doing a project, look up front at what you want to do. Start looking at the guidelines to see does it meet the basic structure of the guidelines. If it does, then do more research. You can talk to the local referee personnel who would be certifying it. You can do all these things and do that research, do that homework before you do an engine swap. If you're just putting parts on, that's easy. Either they're approved or they're not. If we're actually changing an engine or changing a driveline over, say I want to put a small block V8 in a BMW. Can I do that? Legally, yes, I can do that as long as I meet certain provisions. So I can't do any engine into any BMW, but I've got to follow the rules. And by doing that, I can get things done. And so what I can tell you is older vehicles are easier to do this than newer vehicles. And the reason is networking. It's hard to get that Chevy computer to speak German, right? Yeah. So if I am networked and I need that Chevy computer for the engine to talk to traction control, talk to my speedometer, talk to the transmission, that's going to be an issue. On the other hand, if it's an older BMW, maybe I'm going to put in the engine and transmission from a GM, and I don't need to talk to the speedometer. I don't need to talk to traction control. I don't need to talk to those guys because that car doesn't have those things. Now that's real easy. You see, so there's, as a rule of thumb, if you put an engine in a car that's from a different manufacturer, it has to be that engine, that model year or newer. All the emission controls need to come with the new engine. And the engine has to be the same classification. In other words, I can't put a truck engine in a passenger car engine in a truck, and so on. So those are kind of the basic 1-minute rules, Alberto. From there, they do get a little more involved. But no, I've helped people do some really cool engine jobs. Do allowable emission limits change, get stricter every year. No longer. Good news, Rob. I called them out on that, because the emission standards for a 94 Honda were considerably lower than a 2012 Camry. And I said, this is BS. And they said, no, this is the last time we moved them down. And I've not seen them move them since, and that's been 4 years. But no, they were moving them down to justify program changes, because they were saying, hey, most of the cars fail are this year and older. I said, yeah, because you've tightened the standards up to where they're tighter than the cars newer than that. You guys have manipulated the data. I called them on it. And, but that's why they were getting tight. I mean, my Jeep Cherokee is horrible what they've lowered them to.
That is good news. My non-California car kept getting, it was more and more difficult.
Yes. Yeah, no, they've stabilized. There's no plans to move them down any further. And so that is, that's where it stands right now. Because, currently there is a bill. It doesn't hit your Camaro yet. There is a bill. We'll see if it goes anywhere this time. This is like the 6th bill that's been entered to try to roll off some of the older vehicles so they don't need to be smogged every other year anymore. Currently, they're looking at 83. They've tried 30 years in the past. They've tried other things. This is the newest bill. It's still in committee. I'm not overly optimistic, but we see a bill come every year. There's 2 of them right now dealing with smog and registering vehicles. One is if your car has historical plates on it, then it becomes smog exempt. And no, see me Thursday, not Friday, Christopher. And the other is the 1983. So I guess it's Friday for you guys, but I don't want to confuse anyone. So on that note, yeah, we will call it here. I will talk about when we come back tomorrow about calculating the air-fuel ratio, and I will show you the calculator. So you're right, it is your Friday, but it's not mine. But I will see everyone in the morning. Have a great rest of your day. Hopefully you guys learned some stuff today. And if you're a little confused today, the other half of these slides we're going to look at tomorrow, and it's going to make it less confusing.
Thank you.
You always confuse us, Mr. Brian, or at least me, speaking for myself.
I just challenge you. I know I don't confuse you because you're doing so well. I just challenge you.
No, it's okay. Have a great day. Enjoy your seminar or webinar.
You bet. Take care, everybody.
So
Have a
tomorrow we'll have
good
class?
day.
See you
Bye,
tomorrow.
Mr. Brian. Bye,
Yes.
Stephanie. See you next week.
Mr.
Bye.
Brian?
Next week? No, tomorrow.
I was just kidding.
You're scaring me.
I got confused too because since it's our Friday, I'm like, wait, do we have class tomorrow? Okay.
Yeah, we have class tomorrow. I will see everyone tomorrow.
Mr.
Okay.
Brian,
Mr. Brian.
to keep you
Bye,
awake.
everyone.
Bye-bye. See you